Hi everyone, welcome back to chemistry. In this video, we're going to continue talking about some characteristics that we see in these different phases, and then we're going to talk about pressure. So looking at this picture here, we've seen this several times, right? So this is a solid, a liquid, and a gas, and we can compare these things, and we have a little bit. So we've talked about, the shape and the volume of these different types of phases, right? So solids have, a fixed shape or definite shape, right? If I drop this on the ground, it's just going to stay as a cube. It's got a definite volume as well, right? Because I could measure the sides of each of these sides, or the length of each of these sides, and that volume's not going to change, right? It's fixed. It's definite. Liquids are a little bit different. They have an indefinite shape, right? If I pour this liquid out onto a table, right, it's going to kind of disperse and it's going to look a lot different than the shape it's in the container, right? It forms to whatever container it's in or not in. And then the volume, though, it is definite, right? For liquids, if I pour that volume in a graduated cylinder and I measure the volume of that liquid, assuming I didn't lose any liquid, I should have the same volume before and after. So it's got a definite volume. But gases are really special, right? Gases are kind of different because they have both an indefinite shape or unfixed shape and an indefinite or unfixed volume. So what does that mean? When you look at this gas, right, if you put it into a container that does not have a stopper, right, what's going to happen? Well, all of those gas particles are going to come out of the container and fly around the room and collide with each other and with the room's walls and stuff like that. But when they're in the container, they are kind of, bouncing around and hitting each other and hitting the sides of the container. Lots and lots of energy, we said. And likewise, if we even heated this up even more, right, we'd get those gas particles to move even faster and faster and faster and faster and faster, building that pressure in here until eventually this cork could pop off, right? So gases are really interesting that way. I do also, this is new here. So I do want to take a look at that. So this says the characteristic is relative intermolecular interaction strength. So in other words, what is the strength of the intermolecular, can't say that today, forces between these molecules in these different phases? So for a solid, and a good example of this would be something like NaCl, sodium chloride. Usually we find that in the solid form, right? We said that ionic compounds tend to have really strong intermolecular interactions or forces, and this is true. And solids tend to form these kind of crystalline structures or crystal lattice structures you'll sometimes hear, where you've got kind of alternating pluses and minuses for your ions kind of attracted to each other because they like that difference in charge. And it just turns out that this is a really, really strong interaction between these particles. So those solids they have that strong intermolecular interaction. Whereas liquids, they're still somewhat strong, but they're more moderate, okay? They're definitely not as weak as for a gas, and we'll talk about why gases have weak intermolecular interactions. But for liquids, they're kind of right in the middle, between solid and gas. They're still attracted to each other, but they can move around and slide past each other and change position in a way that these just won't in the solid state. And then in the gaseous phase, again, gases are a little bit special. Their intermolecular interactions are really weak, and the reason for that is that these gas particles are really far apart for the most part. They're going to collide with each other and with the walls of the container at times, but for the most part, they're not in contact, those particles, and they're in these kind of random positions because they're constantly moving around. So as we go to the left, right, from gases to solids, our intermolecular forces are increasing. The strength of those intermolecular forces is increasing. But as we go to the right from solid to gas, our temperature or kinetic energy of those particles is increasing, right? The gas particles have really high kinetic energy because they're moving so much. Kinetic energy is the energy of motion, right? So and then comparing that to a solid where those particles aren't moving. So we can sum up these kinds of ideas or observations about gases using something called the kinetic molecular theory. And a gas that follows all of these rules or statements that I'm going to read through with you, that's called an ideal gas. It's kind of a perfect gas. Of course, not gases are real gases, right? They're not always ideal. But an ideal gas will behave in the ways listed here. So, kinetic molecular theory of gases states that gases are composed of tiny particles that are separated by very large distances. These gas particles are constantly moving, experiencing collisions with other gas particles and with the walls of the container. Highlight that as well. The velocity of these gas particles is also then related to the temperature of the gas, right? If we increase the temperature of that gas, the velocity of those gas particles is going to increase as well. And then gas particles, they don't experience any force of attraction or repulsion with each other for ideal gases, right? Because they just are so far apart from each other that they're not really attracted. And if they are coming in contact, it's for such a short amount of time that there's just really weak interactions between those gas particles. So one of the statements above in kinetic molecular theory talks about collisions of these gas particles. So they're constantly colliding with each other and with the walls of the container, but they're in constant motion. And this generates a force. So because these gas particles are constantly moving, those particles are generating forces, and that leads to pressure. And pressure is this property that we can measure for a gas, but not something that we really talk about measuring for solids or liquids, right? You'll sometimes see people talking about, high pressure day or a low pressure day. And what they're talking about is the atmospheric pressure, right? And those are gases that are pushing down on us from our atmosphere. So what are the units of pressure? There are lots of different units of pressure. There are these things called atmospheres, which we talked a little bit about in the gases lab if we've done it already for your class. If we haven't done it yet, we will, so stay tuned. But there's units of atmospheres, and 1 ATM is equal to 1 atmosphere, which is the pressure that the atmosphere on Earth exerts on Earth. Or on us standing on Earth, right? So right now you are under a lot of pressure, specifically 1 ATM of pressure. We can also measure pressure in units of millimeters of mercury. If you've read a barometer before, you might have read it in this way with millimeters of mercury, or sometimes inches of mercury, depending on whether you're looking at, the metric or the imperial system. And this symbol might look a little weird, but let's break it down a little bit. So Hg is mercury, right? That's the symbol for mercury on the periodic table. And then we just put millimeters in front of that. So how many millimeters of mercury is a unit of pressure? And then 1 ATM is 760 millimeters of mercury. So you can write an equality from that, right? You don't need to memorize this. If you ever need to use this equality, and you will, it'll be given to you on an exam. So 1 ATM equals 760 millimeters mercury. 1 ATM also equals 760 torr. Oops. So torr is another unit that we're going to become somewhat familiar with in this class. And actually, let me go ahead and star which ones we're going to mostly focus on in this class. Probably focus on these ones here. Probably not even pascals very often, but I do want to show you them. But generally, ATMs, millimeters, mercury, and torr. So we also have, pascals, which is just yet another unit of pressure. Okay, and on the right-hand column, you can see that we have equalities listed here for how many, pascals or torrs or millimeters mercury is equal to 1 ATM. So 1 ATM also equals 101.326 pascals. Okay, and just like any time we have a unit, you do want to make sure that you're using the correct symbol for that unit. Pay attention to capitalization and stuff like that. These other two down here, the bar and pounds per square inch, PSI and the bar, you've probably seen those at some point if you've looked at, the weather. So you might have seen the writing on the wall, but we are going to need to be able to convert between different units of pressure. So let's go ahead and practice this. And like I said, pounds per square inch, probably less common for us to use in this class, but I do want to show you it anyway. Pascal's also kind of less common for this class, but we'll show you it. Torrs, this will be pretty common for our class. All right, so we want to convert 4.5 ATMs into the following units of pressure. So if we start with what we're given, which is 4.5 ATMs, just like any conversion problem, we can create a conversion factor that can go here. Now, in order to create a conversion factor, we need an equality that relates the units that we're looking at converting, right? We have ATMs and we have pascals. So we need some kind of equality that relates those two units. And luckily we have one. So it turns out that 1 ATM equals 101,326 pascals, or 1,000 or 101,326 pascals. So 101,326 pascals equals 1 ATM. So what conversion factor could we create from that? Yeah, we could have, ATM on the top and pascals on the bottom, or ATMs on the bottom and pascals on the top, depending on what we want to convert to. In this case, we want to get to pascals, so we're going to need to put pascals where? Yeah, on the top. Pascals needs to go on the top of our fraction so that we can cancel out our ATMs. ATM. So we're going to cancel out those atmospheres. And then we're going to have to do that calculation, which I got 455,967 pascals. And then rounding for sig figs, we could probably round that to 460,000 pascals. All right, now torrs, we want to convert, again, 4.5 ATM, that's what we're given, to torrs. So now we need some kind of equality that relates torrs and ATMs. So let's go back up here and we'll find the correct one. So let me get rid of some of this here. So it looks like we're probably going to use this one here. Okay, so 1 ATM equals 760 torr. So let's write that up here. 1 ATM equals 760 torr, capital T. All right, so do we want torrs on the top of our fraction or on the bottom? Yeah, on the top. We want to end up with torrs, so that goes on the top right, T-O-R-R, specifically 760 torrs, and then 1 ATM goes on the bottom, right? That's the ratio, or that's the equality we have for those units. Okay, so we can cancel out those atmospheres, and we're left with units. So 4.5 times 760 is going to give us 3,420 torr. Let's go ahead and round for sig figs. Looks like about 2, so we'll go 3,400 torr. Oops, let me fix. Fix my box there. All right, now pounds per square inch, same idea here, right? We're starting with 4.5 atmospheres. We want to get to pounds per square inch, so we're going to need a conversion factor that relates pounds per square inch to atmospheres. So let's go up here. This is not one of the ones I wrote down, so let's take a look. It looks like we have 14.7 psis, or pounds per square inch, is equal to 1 ATM. So 14.7 psi equals 1 ATM. So we need ATMs on the bottom, and that's equal to 14.7 psi. Can cancel out those atmospheres, and we're left with pounds per square inch, and that's 66.15 psi. Let's round to 2 sig figs, so we'll go 66 psi. All right, so that's how you convert between different units of pressure. In the next video, we'll talk about something called gas laws.